let me start by making a couple of remarks about Gobind. Where's Gobind? There he is. 4 remarks, Gobind. You're going to have to put up with it. 1 personal, 1 professional, 1 technical, and 1 scientific. I started at MIT as a baby assistant professor in 1963. That was before some of your parents were born. And one of the things that those of you who go into, graduate students and postdocs who go into academic careers will find is a remarkable optical phenomenon, which is that when you're in your graduate career, your group cares who you are, your thesis director cares who you are, and you go to be an assistant professor and you become optically transparent. Nobody knows who you are. And one of the things that you remember from that period, and I remember from my first interactions with Gobind, was his unfailing courtesy to me as an assistant professor. Nobody else could even see that I existed. I mean, they all thought I was Herb House's postdoc for years. And that was all right for a while, but after a while it really gets to be pretty tedious. And Gobind, I want to thank you at that point for recognizing that I existed as an independent entity and was not a vapor of some sort. So that's the first point. The second point that I should say is that Gobind has probably had a more important influence on my work, our work, in nucleic acid chemistry than anyone else here. And this is, of course, a broad statement. And the reason for this is the following, that somewhere in the late 60s, Arthur Kornberg, who is another sort of Gobind Khurana class figure, decided that it was an important thing for chemists to get involved with DNA, whatever that meant. And he put together a very nice workshop out in Stanford. He hauled a whole bunch of us out, I think picked out of the phone book. And he hauled us out to California. We learned about DNA for a week. And I got very excited about this. I thought this was a terrific opportunity. And then I came back to Cambridge, and I found out what Gobind was doing. And I decided it was absolutely fruitless for me to go into DNA chemistry. So I never did any. So the impact on my DNA chemistry was phenomenal, Gobind. You absolutely prevented me from doing any. The third, of course, is technical, which is that having not gone into DNA chemistry, we went into protein chemistry. And now, many years later, we, like every other high school student, when we want to clone a protein, we use stuff that depends absolutely on what you and others did. So we're very grateful for that. And then the final remark, again, for students, is actually an important one. And that is that in any period of time, there are a small number of scientists who set the standards for what science means in terms of integrity. And Kornberg was one, and Josh Lederberg was one, and Albert Eschenmoser was one, and I would say my friend Phil Sharp was one, and Gobind, you were one. And so for a generation of people, you said that this is what science does and this is the way it's done, not for career, but for science. And I think we're all very grateful to you for that. So thank you very much. So the problem that I'm going to talk about here is one in which I've listened to what people have been talking about today, you know, stunned by the progress in the field. I've picked this out, Gobind, because it is pre-Gobind Khurana. That is, it's what nucleic acid chemistry was like before there was any nucleic acid chemistry. This is a problem in which we're barely getting a grip on what the nature of the questions are, and I have very little to show in terms of the actual progress in the field. But the question is the opposite of what we've been talking about. Not how do you think about how life as we know it is manipulated, but rather where might it have come from? There's a very, very big question there, which is that we all know that dissipative systems can bring order out of disorder. But the fact that you have a dissipative system does not mean that you necessarily will bring order out of disorder. It doesn't follow that way. And the characteristics of the where does life come from problem is not that we're ever going to know where life came from, but rather can we even convince ourselves that the principles that we now know did this. And what I'm going to say, basically I don't understand how it could have happened. That's not a statement about intelligent design. It just is to say that this is one of those problems that's sufficiently interesting that it's really not clear in a Kuhnian sense that there is an answer. I don't know how to go about it. But the question that we've been asking is a question of, can we do chemistry that even suggests how some of this stuff might have started? And to answer that question, we have to do an initial step, which is to say, what was the chemistry of the environment at the time that life is believed to have started? And that's about 4.3 billion years ago. And this turns out to be quite a complicated task of analysis to even figure out what plausibly the Earth was like at that point. And let me just sketch some of the features of it. The first is that Earth had a lot more water then than it did now. And in fact, it is not obvious and is still a matter of contention as to whether there was any land above water at all. It may have been in a completely fluid planet at that point. At the maximum might be that there was perhaps 5% of the current land mass above water as then as now, but not very much. The second thing is that there were no continental plates. And what that meant, what that means, is that everything was a black smoker. Everywhere that you looked was the equivalent of Yellowstone. There was cracks going down to magma and bubbling minerals and stuff up everywhere. Very different kind of atmosphere in that sense. Extensive volcanism, extensive ubiquitous geothermal activity. The sun was quite cool, but very UV rich. And that's important because with all the water, there was a very high concentration of water vapor in the atmosphere. In the upper parts of the atmosphere, the water was photolyzed to hydrogen atoms, which combined to give hydrogen, and oxygen atoms, which did various things. The hydrogen boiled off. So that the upper atmosphere was very oxidizing. And of course, right below this non-continental plate was molten iron, which was very reducing. And there was an enormous gradient in redox potential, which was the dissipative potential that drove whatever it was that happened. But what we don't know is what the gradient was. And there are various arguments about that. I think everyone agrees it was not oxidizing at the surface. And the ocean at that point was believed to be red, mildly acidic, and reducing red from the dissolved ferrous iron. But it's a completely different environment. Continuing impaction. This was just at the end of the period of what's called the period of heavy impaction, which was characterized by what are known in the trade as ocean evaporators, meaning that one of these things fell into the water, since it was all water, and the thermodynamics of that was sufficient that the ocean evaporated at that point, meaning that the surface of the Earth at that point was covered by superheated steam for a few thousand years, or 10,000 years, and then cooled down. An interesting environment to try to start bringing order out of disorder. Close moon, the moon was probably half as far away at that point. The tides were supposed to be, depending upon how you want to think it, maybe a kilometer high and occurring a couple of times a day. That's a little unpromising as well. The earth tides may have been a couple of meters. The guess is that it was certainly rich in CO2, rich in nitrogen, rich in water, probably not much methane, very little oxygen, probably not much ammonia. The reason this is interesting historically is that the Urey-Miller experiments, which were spark discharges in methane, ammonia mixtures, were very interesting experiments, but probably completely irrelevant with what went on at that point. And then this last issue from the point of view of chemistry is extremely interesting, which is that periodically something would happen with the sun which would take everything that was there and blow it out to about the radius of the Oort cloud, where it would sit and get UV irradiated for a while, and then it would fall back. And so basically all of the organic matter on the surface of the Earth at that point had been to space, had been irradiated, and came back. And what that means is not quite clear, but the chemistry in that environment is one that's at low temperature, very high vacuum, hence dominated by entropy rather than enthalpy, hence completely the opposite of what we're familiar with. I mean, just extremely interesting stuff. To think about this world, we have to think about starting from chemistry from scratch, with some big unknowns. So the interest in this area, and the reason why I think it might be interesting to Gobind, is that what we know now is an enormous amount about life, and by deconstructing, we can build backwards. What we have here at the origins were this chaotic, filthy world. And the question is, how did it get started? My sense is that once you get to a self-amplifying system, you're probably ready to go, and we have an enormous amount ready to do at that point. But how you get there is, to me, one of the most interesting questions in science at this point. Now, why do you care? And this is another interesting question for students. The whole issue is sufficiently interesting that a very fundamental question, which is life on Earth a phenomenon that occurs every time that you have a planet like ours, in which case there are probably a very, very large number of planets around, that's my guess, that have these kinds of conditions, in which case I think we're perfectly entitled to trash the planet any way we want to. I don't think we care at that point. The alternative is to say that we might be a once-per-universe event. And I actually don't think we know which it is right now. I mean, there are people who say that, I mean, the figure, for those of you who like these things, hold up a disk the size of a quarter and look in any direction, you see something like, if you look carefully, we can see something like 10 billion galaxies in that size. That gives you a sense of the number of stars that are around. That's a lot of planets, but we don't have any idea whether we're talking about a 1 in 10 to the 5,000th event, or whether we're talking about a 1 out of every 1,000 event. We just don't have any idea at this point. So that's one of the interesting questions. The second is this question of the spontaneous emergence of order from disorder. Good friends like Jack Szostak are doing a fantastic job of showing how vesicles begin to disassemble themselves, for example. But of course, what you're working with here was something like probably water emulsified with coal tar. And the entropy of concentration of mixtures into something in which chemistry occurs is so horrible that it's not clear that that can work. So I love Jack's work, but how to connect it to something is not quite clear to me. Darwinian selection we understand as one of the big ideas in science probably ever. But can one apply the idea of Darwinian selection to reaction networks, to chemistry? There is an argument, which I happen to subscribe to, that what one wants to think about here is Darwinian catalytic networks. That is, chemistry somehow gets together by unknown principles, and it begins to amplify itself, so that some kinds of chemistry become important and begin to predominate. That gets encapsulated somehow in emulsions, or perhaps in cracks in rocks, and it all gets started that way. Pretty vague, I know. And then there are a series of other very interesting questions, which I won't touch on, other than this, I think, very interesting issue that's going to come up fairly soon now, which is the question of non-living sentience and life without biology. So how does one even begin to think about this problem? And the answer isn't known. This is, as I say, a genuine answer. There are a couple of things that I can point out to you as being interesting. One is that if you look at life as we know it, from a chemist's point of view, and I think that's appropriate here because I'm working on the assumption that it started with chemistry. What you see is something that looks more like a patchwork quilt than a single event. That is, it looks like bits of chemistry that have been assembled from various places. So, for example, let's just take a couple of these things. You find iron-sulfur clusters everywhere in redox chemistry. That's exactly what you expect from deep smokers. It's exactly what you expect. You see these things being formed now, and almost certainly those came from naturally occurring colloids getting wrapped up in organic stuff. Thioesters, Christian Dedeuve has made a very strong case for the importance of these, and I'll return to them. Phosphoanhydrides are everywhere. Lipid membranes occur spontaneously wherever you have surfactants, but probably all these don't go on in the same place. So it looks like life is a bunch of things which make a lot of sense individually, but somehow put together. How did that happen? It's an interesting problem. The things that we need to deal with are the ones that we put here. And the only one I want to touch on here is, what is a search strategy for this? I mean, how does one begin to think about it scientifically? And we have to be careful. The approach that we've taken is one that others also are taking, which is to work on what are called fossils. And the idea in fossil searching is to look at phenomena that occur apparently everywhere, throughout life. So all life uses nucleic acids. All life has potassium rich on the inside, sodium on the outside. All life has lipid membranes. Can you infer something from that? And the argument is that if there's something that seems to be everywhere, perhaps that gives a hint for at least the environment in which things started. I'm going to show you an example of thinking along those lines, but I just want to also show you the risk, because it was something that's come up here. Right now, we make compounds of this sort, which occur in a wide variety of sorts, by a pathway that, there's several different pathways, but largely starts with thioesters, condensation, formation of isopropenyl pyrophosphate, and then polymerization to give things of this sort. It's important to recognize that you can, in principle, make the same kinds of things, not from isopropenyl pyrophosphate, but from isoprene, which could be formed from formaldehyde, which comes out of methane on oxidation. There was almost certainly formaldehyde at that point. And the most stable of the single double bond hydrocarbons, which is isoprene. So isoprene plus formaldehyde over any rock will give some of this, which dehydrates to give that, to give this. So the fact that all of these things are ubiquitous in biology, true fossils, probably is an artifact and has to do with the fact that these proved useful and were recruited by some other pathway later. Maybe. Everything in this world is maybe. But let me show you one example of a subject that we're interested in. And it has to do with the fact that one of the great commonalities in life is that life is rich in potassium on the inside and sodium on the outside. Why is that? Now, this is the kind of thing that chemists and biologists typically don't think about. But if you ask how this kind of happened, an argument is that, well, this is the natural thing to do, because after all, you have an environment which is rich in sodium and poor in potassium, and a very natural kind of battery for that arrangement is to simply concentrate the potassium, exclude the sodium. You then have a concentration gradient which stores energy, and it's a kind of the minimum system that you can have. That's terrific, except that parabiotic chemistry actually didn't know very much about thermodynamics and concentration entropies and things of this sort. So it really isn't clear how that happened. So how did it happen? We have a postulate, a proposal, which is that, if I can put it this way, it happened in Saskatchewan. And how do you arrive at that kind of notion? And that is, you go to, as I have actually personally done in winter, you go to a place called something up in there, and Saskatoon, where it is really, really cold. And then you go south from Saskatoon a bit, and then you dig down by about 1,000 feet, and you get to a salt mine. And this salt mine is clearly, it's outlined here, and it's clearly the evaporate of a sea that evaporated at some point. And what's interesting about it, and something which you also see in some seas now, but not in all, the Dead Sea shows some of it, others don't, is that in this particular sea, it's 1,000 feet of sodium chloride and 10 feet of potassium stuff on the top. And the hint in that is that what one had was a sea, which is perfect in a sense, if you think about an origin of this kind of thing, that evaporated, a dying sea. So as it evaporated, several things happened. One was the top layer of fluid became potassium enriched because of solubilities. And also, this was where all kinds of thermal activity was going on. It was bubbling manganese and copper and iron salt, sulfides as colloids into it. the formaldehyde and acetylenes and nitrils were raining in from outer space. The whole thing was probably being stirred by these gravitational forces. It sounds like a perfect place to have all kinds of chemistry going on. So it makes sense. Is there any sense that this might be right? And the answer is, indeed. If you just simply take potassium-sodium mixtures with various anions and you concentrate them, what you find is in the final analyte, if you start with a 1-to-1 mixture just for the sake of this simple illustration, you end up with carbonate and phosphate with potassium and sodium ratios that are in the order of, they can get up to something like 10-to-1. Now there's another interesting thing about that. So that, this is an argument that these upper reaches are in fact, you can get enrichment in potassium, and there's something else which is interesting about that. The salts that tend to concentrate there are potassium and carbonate as an anion, and also phosphate as an anion. Now, why is phosphate interesting? Well, of course, phosphate is another one of those elements that's really, really important in biology. But there's something else about it. And that is that, as some of you may remember from your first year chemistry, there is a word called deliquescent. Deliquescent. I suspect that many of you have forgotten what the word deliquescent might mean. If you crystallize sodium chloride, what happens is that you get crystals of sodium chloride, you evaporate off the water, it's all gone, crystals of sodium chloride. There are salts from which you cannot get the water to evaporate without really heating the stuff up. And if you, in fact, put them under normal conditions in contact with atmospheric conditions, they suck up water. That is, they are spontaneously hydrated, deliquescent. And it turns out that the deliquescent salts are potassium phosphates. So that leads to a kind of picture. Let's see, you get my picture here. The picture is in which in this sea, what you have is potassium on the surface, phosphate running in. You get this mixture of potassium phosphates and carbonates, which are deliquescent, sitting on hot rocks. When you sit them on hot rocks, they evaporate, they begin to dehydrate and make phosphoanhydrides. So you now have phosphoanhydrides with potassium salts in an environment that has lots of organic stuff, so that it begins to cover itself up with manganese and iron sulfides wrapped in organic material, and so on. Now, this is all hypothesis. It has nothing at this point to do with anything. But what I can say about this is that I think that it is beginning to assemble a picture of a world in which one can think about the chemistry. That's the best I think that we can say at this point. But I think that the right place for chemists to begin to ask about reaction chemistry is this kind of concentrated salt solution, rich in potassium, rich in carbonate and in phosphate, containing catalytic colloids, probably with a lot of formaldehyde from partially oxidized hydrocarbons, and then a lot of other stuff like acetylenes and things like that coming down. And in fact, if you look at this environment, you can begin to do some really interesting chemistry. So this is prebiotic chemistry before anything has happened. We don't know anything. And that's pretty much the way the world was before Goban Corona began to build things. And so I'm immensely grateful. We are all grateful for what you've done, and who knows, you and I should live for 100 years and see what happens with Origin of Life. Thank you very much.